Welcome back. And so we're in this process of dissecting this guiding question of statistical inference. And so we're investigating that blue question. How can we do inference with a sample so that it makes sense? And we saw with law of large numbers, one way is if we're looking at the population mean, just increase the sample size. Sample size really will kill everything else, and it'll dominate, and it will give you what you want. Okay, because again, as you're increasing the sample size, you're getting more and more people in your sample, and therefore getting a bigger chunk of the population. Okay, but I mean, how realistic is it to sample 1 million people on a certain characteristic? Well, probably not, right? Um, so then what? Okay, and so what we can do is a different technique where we try many different samples of a fixed sample size, and usually the fixed sample size is smaller than what we would normally expect. Okay, and then just for now, we're imagining that we're doing this without replacement. If we're doing replacement, then we call that bootstrapping. Okay, so the idea here as a diagram is that we have, a population that we're trying to, a population parameter that we're trying to make an inference on. Maybe it's your population mean, mu. Okay, and what we do is we look at a bunch of samples. So sample 1, sample 2, oops, sample 2, and then many more. And maybe this is like sample 1000. Okay, and within each of these, right, we maybe look at that unbiased estimator, x bar, in each of these, okay, and use that to compare. So we kind of compare. I'll just maybe connect all of them and use that to make some sort of inference on the population mean. Okay, I should also mention that this 1000 here would be our sample, it wouldn't necessarily be our sample size, but we could also use that as n. Okay, um, so just something to be aware of. But nevertheless, let's see this in action. So I'm going to look at Excel example 2. All right, so what I've done here is in Excel example 2 here, I've created many SRSs, 50 SRSs. Okay, so that would be those, bubbles 1 through 1,000 that we just saw. Okay, and within each SRS, okay, there's a formula in there. You don't really know what it means yet, and that's fine. But each of these SRSs is, what, 32 unit or 32 individuals or observations per sample. Okay, and what I did is I calculated x bar for each sample. Okay, well, that was fun. Okay, and then just for reference, I computed the min and the max. Don't really need it, but what I'm going to do now is look at those x bars, okay, and use those to hopefully say something about the population. Okay, now just for reference, I made a graph that shows the distribution, or the yeah, I guess, yeah, distribution of the x bars, and then I also did it for samples 1 and 2 just so you can see it. Okay, and that graph is right here. Oops. So let's take a peek. Okay, so it's a little big, but it's fine. So you can see the gray is the sample means, and then samples 1 and 2 are the blue and orange respectively. Okay, so as we look at this, what do we notice? So I just want you to take a minute to look at this and think about the different pieces of language we have with histograms. So like shape, center, spread. Okay, and just take a minute, pause the video, and see if you can talk to yourself about the shape, center, and spread. Okay, well, as I look at the sample means, right, the gray bars in comparison to the other two, first, in terms of the shape, I notice that they're a little bit more normal. Okay, at least it looks like a normal curve, and well, I've been seeing normal because, well, we've been working with the normal distribution, right? So, but anyway, it's at least unimodal. Okay, Whereas the other ones, the orange is maybe bimodal, and the blue is maybe unimodal, maybe bimodal. Okay. We could also resample and just see how things change. Okay. So either way, as I change the sample, that behavior with the gray bars of being roughly unimodal and roughly symmetric is still present. Okay. While the other ones, while the blue and the orange shift around a lot, I also noticed that in terms of spread, the gray bars are less spread out than the orange and the blue. Okay, so I've talked about shape, I've talked about spread. Where's the center? Okay, do the centers seem to shift? Okay, for the gray bars, not really. Okay, and following this down, the center appears to be between 9 and 10, or so I think. Um, and if I continue to resample, just hitting Fn F9 on my laptop, or you just hit F9 on another computer, um, that behavior seems to still stay the same regardless of the samples that I choose. Okay, so I've talked about shape, center, and spread. And so what we're doing here, this process of looking at the means to make an inference is, well, when I look at the sample means, they seem to, gravitate around this mean of between 9 and 10. So maybe that's a good inference to make, is that the population mean is about 9 or 10. I'd have to, do a little bit more analysis there. Nevertheless, I can say something meaningful because I've done this process of collecting many samples, looking at the statistic from those samples, and using those statistics to make an inference about the population mean. Okay, and this process is actually statistically valid, and it's known as creating a sampling distribution. Okay, so just so we're clear on the two different pieces of language here, before we have seen a probability distribution. Back in chapter 9 and 10, when we saw like the table where it was x and then the probability, and then we had, da 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 da, that's a distribution. Okay, all a distribution is, or probability distribution is, it's a way to assign probabilities to the different outcomes in the space. That's all a distribution is. Okay, when we talk about a sampling distribution, that's different. Okay, we have to be careful of the language here too. It's a distribution of the values of a statistic. So think it's a distribution of x bar. Okay, so it's telling me how x bar in the example we just saw is distributed for all possible samples of the same size from the same population. And that's really crucial. So my same size here before, I believe it was 32, right? I had 32 kind of rows, and then I had 50 iterations of that same thing. And I did use the same population. It actually came from a chi-square distribution, which we'll see later in the course. But nevertheless, everything came from the same population. Okay, so a sampling distribution of a statistic, of x bar, of s, of p hat. Okay, so and I talked about these observations, but I noted that when I looked at the sampling distribution, it seemed more normal, and that's actually a common trait. So it's going to be rough. It's going to be more normal, and consequently, you can use the same language from normal distribution. So symmetric, unimodal, bell-shaped, all that applies. Center is that it should be centered around the population parameter. Okay, assuming you have good samples. Okay, assuming you have an SRS and all that good stuff. Okay, and the spread, this should be greatly decreased. Decreased from the sample. Okay, because again, when we look at say the means, for example, if we look at the spread of the mean is already brought in those extreme values. It's already it's already taken into account those extreme values, so we should see less shift or less overall or less extreme values occur. I'll say that. Okay, so we see less variation, and this gives us more normal behavior. And with that, once we have normality, that's actually really interesting. Then we have a lot we can do with it, as we saw in chapter 11. Okay, so there is a theorem that kind of summarizes this behavior from sampling distributions, and so we'll talk about that in the next video.